Hello again. Today we will answer the advanced study assignment for the molar volume of a gas experiment. Just a reminder, the advanced study assignment calculation are similar to the lab report calculation. So let's look at these questions and let's see how to answer them. The first question states, write the balanced molecular and ionic equations indicating the state of each species in each equation for the reaction between magnesium solid and HCl or hydrochloric acid. So this is the reaction that will be done in the experiment. So the question is asking for three equations, the molecular equation, the total ionic equation, and the net ionic equation. So first let's begin with the molecular equation. So here we are reacting magnesium solid plus hydrochloric acid aqueous. This is going to yield, now this here is a single displacement reaction, which will also be a redox reaction. Okay, so the magnesium here will replace the hydrogen. Okay, now magnesium is an alkaline earth metal, and when it's ionized or when it's oxidized, it's going to lose 2 electrons and it will become a +2 ion. Okay, so when it combines with chlorine or with Cl, it will become MgCl2 subscript 2. So this is magnesium chloride, and the protons from the acid will be reduced to hydrogen gas. So the hydrogen gas that we see in the experiment comes from this reaction. Okay, so this here is a molecular equation, but we do have a problem. The equation is not balanced. We see that we have 2 Cl's on the product side. We only have 1 on the reactant. We also have 2 hydrogens on the product, but only 1 on the reactant. So here we'll need a 2, okay, in front of HCl to make this a balanced equation. Okay, now we could move on and go to total ionic. In total, just a reminder, in total ionic, all solids, all liquids, all gases remain as they are. They cannot be broken down into ions. Only strong electrolytes can be broken down into ions, such as HCl and magnesium chloride. So the total ionic equation here will be magnesium solid will remain as it is. HCl will break down into ions, will ionize. This exists in solution as H ions, hydrogen ions, plus chloride ions. And because there's a coefficient 2 in front of it, I need to indicate that in my total ionic equation. I'm done with the reactants. Now I will turn over to the product, and in the product I have magnesium chloride aqueous that will also break down into ions, which will give me 1 magnesium ion plus 2 chloride ions. Hydrogen is a gas, so that will remain as it is. Okay, and now what I will do is I'm going to look for spectator ions. Okay, and for the spectator ions, magnesium is not, because here in the reactant I have magnesium solid, but On the product, I have magnesium plus 2 ions. Hydrogen also, it's not, because they exist as ions in the reactant, but they exist as a diatomic molecule in the product. The only spectator ion that we have is chlorides. I have 2 chlorides in the reactant side, as well as 2 chlorides in the product side. So they cancel out. Okay, so now what's left is my net ionic equation. Okay, and my net ionic equation will be the heart of the reaction, and it will be everything else that did not cancel. So here I have magnesium solid plus the 2 protons from the acid. They will yield magnesium ions plus hydrogen gas. Okay, so this here is a redox reaction. We can see that magnesium is being oxidized. It's losing 2 electrons, and hydrogen is being reduced. H plus ions is being reduced to hydrogen gas. And this is the heart of the reaction. This is really what the reaction is. The spectator ions are just there. They're exactly as they're named. They're spectators. Okay, let's move on to question number 2. Question number 2 says, the density of hydrogen gas, H2 gas, at STP has been measured to be 0.08988 grams per liter. First part of the question asks for calculate the molar volume of this gas at STP. So we're being asked to calculate the molar volume at STP. We are given the chemical formula for hydrogen gas. It's a diatomic molecule, so it has 2 atoms of hydrogen, and we are given the density at STP, which is 0.08988 grams per liter. So there are 2 methods to answer this question. The first method we can use is the density equation. Density equals mass over volume. Okay, so let's start with this equation first. Okay, so the density equation is the density of a substance equals its mass over its volume. Okay, well, we're being asked for volume. We have the density, and we have the mass, but indirectly. We know that the mass of hydrogen is H2. Each atom of hydrogen, if we look on the periodic table, weighs 1.008 grams per mole. So if I have 2 atoms of hydrogen, the mass of hydrogen gas will be 2.016 grams per mole. So this here is mass of H2. Okay, so I can rearrange the equation. I'm looking for volume. Volume will equal to mass over density. The mass of hydrogen, we determine it from the periodic table. It's 2.016 grams per mole. The density of hydrogen was determined experimentally, and that is 0.0988 grams per liter. Now, if we look at the units that cancel is grams. I have grams here, I have grams here. Okay, so the grams cancel. If I look at the other units, okay, the other units don't cancel, but on top I actually have per mole in the numerator, and on the bottom in the denominator I have per liter. So here they're inversed, so what I will do is I will inverse the units, so it becomes liters over mole, which are the units for molar volume. So this tells me that here I'm on the right track to find the molar volume. Next, I could get my calculator and calculate what 2.016 divided by 0.08988 grams per liter are, and I will get a very long number on the calculator, 22.42990,654. I am limited on 4 significant figures because the numerator is 4 sig figs and the denominator is 4 sig figs, but I'm going to cheat a little bit and I'm going to add an extra significant figure, and I'm going to keep it 5 because second part of the question is asking me to compare it to the molar volume of an ideal gas, which is actually a 5 sig fig number. So here I'm going to round this up to 22.430. So this is the first method that we could use. The second method we can use, let me do this in a blue pen. Okay, I don't have to remember the equation, but if I keep my units constant and I cancel out what I don't need, then I'm able to arrive at the same answer using a different approach. Okay, now if we look at the problem, I'm given the density. The density here is grams per liter. I have the molar mass of hydrogen in grams per liter. I'm asked for molar volume, and I know that molar volume has a unit of liters per mole. So I want my liters to be in the numerator and my moles to be in the denominator. Okay, so what I need to do, okay, is if I look at the density is given as 0.08988 grams per liter. So I could write this as 1 liter of hydrogen gas over 0.08988 grams of hydrogen gas. So basically, I inversed the density. So instead of having grams over liters, now I have liters over grams. And the reason why I have liters, I inversed it because molar volume really has liters in the numerator. So I'm trying to maintain that, and by keeping liters in the numerator. I'm going to multiply this. Now here, if I look on the denominator, the denominator is moles for molar volume of a gas, but right now I have grams of hydrogen. So what I will do is I need to cancel grams of hydrogen and replace it with moles of hydrogen. Well, grams of hydrogen over moles of hydrogen, that's really the molar mass. And I have the molar mass. The molar mass of hydrogen is 2.016 grams of hydrogen per mole, so that means it's per 1 mole. And this allows me to cancel, let's get a different color. This allows me to cancel grams of hydrogen. Okay. And now I could calculate. Now if you look carefully here, well, this is going to be the same exact calculation we entered in the calculator for the top calculation. So it will give me the same answer, 22.430. The units, the numerator is liters of hydrogen. The denominator is moles of hydrogen. So we get the same answer, but using two different methods. Okay. Now, so we determined the molar volume of hydrogen gas at STP experimentally. Now, part B asks to calculate the percent deviation of this value of the molar volume of an ideal gas. And the ideal gas has a molar volume of 22.414 liters per mole. This is a value you should really memorize. Okay, it's a very useful number to know. Okay, first, well, what is percent deviation? Percent deviation is really another fancy way of saying what is the percent error. Okay, so the equation for percent deviation is equal to the experimental value minus the accepted value divide by the accepted value multiplied by 100. So my experimental value, well, that was determined in part A of the question, 22.430 liters per mole. The accepted value is that of an ideal gas behavior, which is 22.414 liters per mole. So I can start entering my numbers in the equation, and I would have 22.430 liters per mole minus 22.414 liters per mole divide by 22.414 liters per mole multiply by 100. Okay, we can calculate the numerator now. Usually the percent deviation, we do the absolute value of the deviation to not cause confusion. Okay, but you could also leave it, okay, as a positive or negative percent deviation. Usually a positive percent deviation indicates that your experimental value is higher than the accepted value. A negative percent deviation means that your experimental value is lower than the accepted value. Here we will have a positive percent deviation because my experimental value is higher than my accepted value. And if I subtract 22.430 minus 22.414, I will get 0.016 liters per mole. I will divide this by my accepted value, which is 22.414 liters per mole multiplied by 100. Okay, you will get again another long number. I'm gonna only keep two significant figures, so the answer will be 0.071%. So this here is a positive error indicating that my experimental value is above the accepted value. Okay, let's move on to question number 3. Question number 3 has two parts, part A and B. Part A states a reaction of 0.0825 grams of magnesium with excess hydrochloric acid generated 84.6 ml of gas, hydrogen gas, H2 gas, at 22.5 degrees Celsius. The gas collected by water displacement in a 22.5 degree water bath above a column of water that is 113.0 millimeters of water. The barometric pressure in the lab that day was 772.4 millimeters of mercury. Use Dalton's law and the vapor pressure of water at 22.5 degrees Celsius to calculate the partial pressure of hydrogen gas in the collecting tube. Okay, so first the question is asking about using Dalton's law of partial pressure. So first we need to state what Dalton's law of partial pressure says. Dalton's law of partial pressure states that the total pressure is equal to all partial pressures. It's a very simple law. Okay, so now we can go ahead and look at our experimental setup. We are reacting magnesium metal with hydrochloric acid to produce hydrogen gas. Hydrogen gas is being displaced by water, okay, and collecting in a tube called a eudometer. Okay, so the total pressure that's acting on the system right now is the barometric pressure. Okay, that's the total system that's acting on the surface of the beaker. Okay, and that is our 772.4 millimeters of mercury. The pressure that's opposing this pressure is everything that's inside the eudometer from the surface of the beaker up. Okay, and if we look inside, we have a few things inside the tube or inside the eudometer. First, we have the pressure, the partial pressure of hydrogen gas that was produced from the reaction of magnesium hydrochloric acid. This gas is wet gas, it's not dry hydrogen because it's collected over water, so it will contain some amount of water vapor. The amount of water vapor depends on the temperature of the water. The warmer the temperature, the more water vapor will exist. Vapor pressure will exist. The lower the temperature of water is, the lower the pressure of a water vapor. Okay. Next thing that's opposing this pressure is also this column of water. And this column of water is measured to be 113.0 millimeters of water. Okay. So the total pressure, which is 772 millimeters of mercury, okay, is opposed or equal to the pressure of the partial pressure of hydrogen gas plus the pressure of water vapor plus the pressure of this water column. Okay, so to find out the vapor pressure of water, okay, we need to look on page 2 of the handout, or you could look at an appendix in the back of the book, and we have a table in our handout for the vapor pressure of water. Okay, and here we are interested in the vapor pressure at 20 degrees and at 25 degrees, and the reason for that is because our water bath temperature is 22.5 degrees, and 22.5 degrees is between 20 and 25. Okay, so here I see that at 20 degrees Celsius, the vapor pressure of water is 17.54 millimeters of mercury. At 25, it's 23.76 millimeters of mercury. So I know that at my water bath temperature, my vapor pressure of water will be between these two measurements right here, 17.54 and 23.76. So first, let's start with stating Dalton's law of partial pressure. So Dalton's law of partial pressure says that the total pressure is equal to all partial pressures, and in our case for this experiment, those pressures consist of the pressure of water vapor plus the pressure of the water column let me fix this plus the pressure of hydrogen gas. Okay, we'll begin with looking at the vapor pressure of water. Okay, so for the vapor pressure of water, what we need to do is look at the vapor pressure table that we have. Okay, it's on page 2 of the handout. Also, you could look at an appendix in the back of the textbook. Our vapor pressure here is 22. We're looking for the vapor pressure at 22.5 degrees Celsius because that's what our water bath is. So the warmer the water, the higher the pressure, the colder the water, the lower the vapor pressure. So let's begin calculating the pressure of water vapor. Okay. Our temperature is 22.5 degrees Celsius, so this here will be between 20 degrees Celsius, where the pressure at 20 degrees Celsius is 17.54 millimeters of mercury, and 25 degrees Celsius, where the vapor pressure is 23.76 millimeters of mercury. Okay, we need to know exactly what the vapor pressure will be at 22.5, so here we could estimate that it will be between 1754 and 23.76, but we need an actual accounting for it, an actual measurement, so we will calculate it. So we will need to know how the pressure changes per degree Celsius, and in order to do that we need to take the difference between the pressure, the difference between the degrees, and divide them by each other. So this can easily be done by saying 23.76 millimeters of mercury minus 17.54 millimeters of mercury will be divided by the difference in the degrees in the temperature, which is 25 degrees Celsius minus 20 degrees Celsius. If we do the math, we see that this here is 6.22 millimeters of mercury over 5 degrees. Okay, we could even further get it per degree, so that would be 2.44 millimeters of mercury per degree Celsius. Okay, now I know that 22.5 is 2.5 degrees away from 20. I already know what the pressure is at 20. It's 17.54, and between 20 and 25 the pressure will change by 1.244 millimeters of mercury for every degree. So in 2.5 degrees, the difference between 20 and 22.5, I could calculate the pressure that will increase. It will increase by 1.244 millimeters of mercury per degree Celsius. The degrees of course cancel. You're left with pressure, and the exact pressure here will be 3.11 millimeters of mercury. Since I already know that at 20 degrees My vapor pressure is 17.54 millimeters of mercury. If I add an additional 2.5 degrees to it, that will change the pressure or increase the pressure by 3.11 millimeters of mercury. I could now add these two, 20 plus 2.5, that will give me 22.5 degrees Celsius, and the pressure here, if I do the math, it becomes 20.65 millimeters of mercury. So that means I already know that my total pressure is 772.4 millimeters of mercury, and my vapor pressure, that's my total pressure, my vapor pressure is 20.65 millimeters of mercury. So there's only one more measurement left before I'm able to calculate the pressure of hydrogen gas, or the partial pressure of hydrogen gas, and that here is the pressure of water column. And in order for me to find the pressure of the water column, let's do the pressure of water column here. So this is the pressure of water column. I need to look up two densities. First, the density of water, and the density of water is 1.00 grams per ml. I also need to look up the density of mercury, which is 13.6 grams per ml. The reason why is I have my water column in a unit of millimeters of water, but it seems that everything in my equation is millimeters of mercury, so I need to convert this millimeters of water to millimeters of mercury so I could add and subtract all of the units, okay, without a problem. So I need to convert between millimeters of water to millimeters of mercury. Okay, so if I look at the difference between mercury and water, mercury is 13.6 times heavier than water. So in order for me to convert from millimeters of water to millimeters of mercury, I need to divide by the factor of 13.6, the difference between their density. Okay, so here the pressure of the water column is equal to 113 millimeters of water, and remember this has to be measured in millimeters of water, not centimeters of water. I'm going to divide this by 13.6. If I do the math, this gives me 8.31 millimeters of mercury. Of course, mercury, since mercury is more dense, the height of a mercury level will be much smaller than water. That's why mercury is used for a barometer versus water, because if we had to use water for a barometer, we would need the barometer to be a height of a building. Okay, so now I found, okay, the pressure of the water column, and that's my 8.31 millimeters of mercury. Okay, what's left is just my pressure. The only pressure that's needed now is the pressure of gas, okay, because Dalton's law states that the total pressure is equal to all the partial pressures. So I already have the partial pressure of water vapor, here 20.65 millimeters of mercury. I have the pressure in equivalents of millimeters of mercury for the water column. It was 113.0 millimeters of water. That will be equivalent to 8.31 millimeters of mercury. And now I could calculate and say that the pressure of hydrogen gas will equal 772.4 millimeters of mercury minus 20.65 millimeters of mercury plus 8.31 millimeters of mercury. And now you see all of the units are the same, so I could add and subtract them without a problem. And if I do the math, I find that the pressure of hydrogen gas is 743.4 millimeters of mercury. And that would be the final answer for this part of the question. The next part of the question states, use the combined gas law to calculate the corrected volume of H2 gas at STP. Be sure to watch your units for temperature and pressure. Okay. Now this is a continuation of part question 3A that we just answered. So before we discuss what combined gas law is, let's see where the combined gas law is coming from. First, it's coming from Boyle's law and Charles' law. Boyle's law states that P1 V1 equals P2 V2. Charles' law states that T1 over T1 equals V2 over T2. If we combine these two gas laws together, we get the combined gas law. And the combined gas law states that P1 V1 over T1 equals P2 V2 over T2. Okay, so now that we have the combined gas law, well, we have two situations here. We have situation 1, we have situation 2. So we need to decide which situation will be for experimental and which one will be for STP, standard temperature and pressure. Okay, well, we could look here. We are, I'm gonna pick, it doesn't matter which one it is, you could randomly choose. Okay, I'm gonna pick one to be my experimental. So here I'm gonna say P1, that's the pressure of hydrogen gas that I found experimentally. V1 is going to be the volume of the gas experimentally, and T1 will also be the temperature of the gas experimentally. Now you could look back at part A to find these. Okay, P1 is what we solved for in 3A, and the problem has the volume of the gas. It also has the temperature of the gas in degrees Celsius, and if you remember, we solved that the pressure of hydrogen gas is equal to 743.4 millimeters of mercury. So we can start to write these down. So the pressure experimentally was 743.4 millimeters of mercury. The volume is 84.6 mLs. We don't need to convert it to liters. We could leave it as mLs. Okay, the temperature of the gas was 22.5 degrees Celsius. This I need to convert to Kelvin. So I'll need to add 273.15, which will give me a 1 decimal place temperature, which will be 295.7 Kelvin. Okay, and now I could, let me get a different color. Okay, I could look up my P2, V2, and T2. Okay. Well, this here will be my standard temperature and pressure. Standard temperature and pressure, well, standard temperature is 0 degrees Celsius, okay, or 273.15 Kelvin. Because if we're talking about 0 degrees Celsius, if we add 273.15 to it, it will become 273.15 Kelvin. Pressure, okay, standard pressure is 1 atmosphere, which also 760 millimeters of mercury, and I would like to use millimeters of mercury because my answer from part A is in millimeters of mercury. So this here is 760 millimeters of mercury. I am looking to correct my volume of hydrogen at STP. So V2 is what I'm looking for. Okay, so I have my equation, my combined gas law, let me rewrite it. P1 equals, P1 V1 over T1 equals P2 V2 over T2. Okay, and I am looking for V2. I'm looking for V2 right here. Okay, so I could rewrite the equation. Okay, rewrite the equation and say that V2 will equal to P1 V1 times T2 over P2 T1. Okay, now I could plug in the numbers. Okay, and P1 is 743.4 millimeters of mercury. And let me fix this 3 times V1, which is 84.6 milliliters, times T2. T2 is 273.15 Kelvin over P2. P2 is right here, 760 millimeters of mercury times T1. I'll write T1 here, which is 295.7 Kelvin. Okay. Before I do the math, let's look at our units. We see that millimeters of mercury cancel. We see that Kelvin cancel. Okay, the only unit that's left is millimeters of mercury. And now I can go ahead and do the math. And when I do the math, I find that the answer is 76 0.4 milliliters of mercury. Okay, that's the final answer. It makes sense because at room temperature, gas will be more expanded, will take on a larger volume, 84.6 mLs, versus at STP, when the temperature is 0 degrees, the gas molecules will be much closer together and they will take on a smaller volume of 76.4 degrees. Okay.